Well, it looks like I just made this video and the microphone was off. So I've been talking to myself for 20 minutes. So here I am. Now I'm doing a voiceover because it's a good video. This is Linear Algebra video 6. You're watching it on September 14th. And we're looking at Rn and subspaces of Rn. And so we start with a definition. So any subset of Rn that has these three properties first, you got to have 0 in there, the 0 vector. Second, for any, that symbol means for any, u and v, and that symbol means in h. So for any u and v and h, the sum is in there, so it's closed. It's closed under addition. And for any u in there and a scalar c, the scalar times the vectors also. So this thing is closed under addition and closed under scalar multiplication, and the 0 vectors in there. So here's an easy example. Take any vectors, doesn't matter how many there are, and you create the span of those vectors. This makes a subspace. And yes, I left this as an exercise for the reader. So if you take any line that doesn't intersect the origin, like a vector that doesn't have a 0 as an endpoint, and you look at all the linear combinations of that, you just stay on the line, and you never get a subspace because 0 is not in there. And that's one of the three. That is one of the three things you have to have there to be a subspace. So yeah, now we've defined subspaces, and next we're going to define what the column space of the matrix is. So yeah, you take the columns in a matrix, and you look at the span, all the linear combinations of the columns, and this gives you the column space. It's always a subspace of Rm. So here you have n columns and m rows, and these a sub i's are the vectors of a1 through n, which are in Rm. Should be capitalized. Column space of A is the span of the a sub i's. And the only time the two are equal was when it spans Rm. Otherwise, it's just a subspace of Rm, and it's not the whole thing. So here's a pretty good example. And I hope this thing is recording. If I have to do this a third time, I'm going to be upset. All right, so we've got a 3x3 matrix A and a vector B and R3. And the question is B in the column space of A? So you make the augmented matrix with A and B, row reduce it using your handy dandy, whatever you use. Make sure you input everything correctly. That's usually where things fall apart. Does this one have a row of zeros? Yeah. All right, so the matrix is consistent, so that means what? B is in there. In fact, there's a bunch of vectors that map to it. So now the question is, is the column space of A equal to R3? And I went ahead and, there's a spelling mistake. Oh, I hate that. That's supposed to be invertible, not invertible. So A is not invertible because when you row reduce it, you get a row of zeros. So that means, it means the determinant's zero, and that means I'm trying to figure out how to do the IMT, which is new for me in my little weird handwriting in this Apple Pencil. But since it's not invertible, the columns in A do not span R3. Therefore, the column space of A is not equal to R3. There's another question. So if this thing doesn't cover all of R3, can we find a vector that's not in the column space of A? This is probably where you might understand what I'm talking about with column spaces a little more. Because the column space of A is a subset of R3, and there's a lot of vectors in there, infinitely many, but not all of them. And all I did was go into my program and start picking vectors on the right changing them until I got an inconsistent matrix. And this one, C, is the one that worked. There's a bunch that work. And so the row-reduced echelon form of AC was 1 dash dash 0 1 dash. Doesn't matter what's in there. 0 0 0. And then on the right hand side, dashes, and doesn't matter what's there. But that bottom row says 0 equals 1, and that means inconsistent. So that means C is not in the span of the column space of A. It's not in the column space of A. Because 0 is not equal to 1. Right. Now we define the null space. And if you really, really want to get confused, ask me how I learned about the null space. Steve Pierce was my professor at San Diego State, and he was a really smart, good guy, but the way he defined it is ridiculous. I like this so much better. So yeah, the null space of A is just all the vectors that map to 0. And I think of this as a linear transformation because A is always linked to a linear transformation. So this takes it from Rn to Rm. Yeah, and the null space is a subspace. I think it's actually a theorem in the book. I just made it a note, but that's another one I'll leave as an exercise. Kind of thing I like to ask on final exams. Yeah, A is M by N, so the null space of A is a subspace of Rn. And the last definition, and this is a biggie, where I finally get to define what a basis is for a subspace. And later on, we'll talk about vector spaces, which is really what we want to get to in this course. We talk about bases for a vector space, which is what a subspace is, but we're just looking at Rn. So whatever the basis is for whatever subspace we're working in, it has to have two things. It's got to be a linearly independent set, and it has to span H. All right? Both of those things have to happen. So you show linear independence and you show spanning. That was my job for years. The spanning part seems to be harder than the linear independent part. And I think now I do a great big example here, and it'll tie everything together. I didn't do the one that Lay did in the examples in the book. I picked one out of the exercises just to have something a little different. And I think his was a 5x5. I didn't feel like working with a big, huge matrix. This one's big enough. So there's the matrix. And, we row reduced it straight away. It's always the first step. Tells us everything we need to know. It's like getting to the atoms of a species. And there's our row of zeros. That makes it fun. Okay, so the column space of A is a subset of R3. So it's coming from the left. And if I have time, I'll prove why this is true, but Yep, the column space of A is a subset of R3. And the null space of A is a subset of R4. And again, if you want to be completely confused, ask me how I learned this. So first we're going to find a basis for the column space of A. And this is just cool. I don't know if I can prove it to you, but I'll try. Maybe in another video or when we meet on Friday. But when you find the columns of A that are the pivot columns, you get that from the row reduced echelon form. The columns in A, not the ones from the row reduced form, the actual first vectors in A that are pivot columns turn out to be the basis. And they correspond to the basic variables. Hence the name basic variables for the basis. All right. So I switch to some color. There you go. There's pivot column 1, pivot column 2. So pivot column 1 corresponds to column 1 of the matrix A, that's 4, 6, 3, and pivot column 2 goes to 5, 5, 4. So those two vectors make up the basis for the column space of A. I'm not sure if I wrote this down, but I guess I probably asked the question while I was writing this and talking to the walls. The column space of A is certainly a subset of R3, but it doesn't span R3 because there's only 2 vectors in there and you need to have 3. So now we're going to find a basis for the null space of A. All the vectors that map to 0. So we've been doing this all semester so far, and we did it in DiffyQs. You look for the 2 free variables, and you just find the solutions. Oops. Go away. There you go. So I do this every time. Some of you are sort of skipping around here. I write X, it's a 4x1 vector. I always rewrite the free variables first because that tells me they're done. You've sorted those, they're free. And then you look at the top for the dependencies. So row 1 gives you x1 equals 4x3 minus 7x4. And row 2 gives you minus 5x3 plus 6x4. And then just like before, you unravel. You just pluck off the x3 terms, including zeros. 4 minus 5, 1, 0. Minus 7, 6, 0, 1. Oops. Erase. There you go. All right, we're almost finished. So the basis is, it's a subset of R4. So the basis for the null space of A is these 2 vectors. And all the linear combinations, all that means is basis. is a subspace of R4. And it certainly doesn't span R4. There's only 2 vectors in there and you need to have 4. All right, well here's the 4th homework set. It's going to be pretty long, I can tell. So I'm glad the last one was short. But this is really important stuff that we need to get through, and it's actually super cool. So if you get into it, it won't seem like a long set. So we're going to work 2.8 and then 2.9 will be the next video, and there'll probably be just as many problems there. Yeah. And if you got anything to do, if you're free Monday night, remember I got office hours from 7 to 8. So if you want to get a jump head on this, you can see the video on Monday and come see me Monday night. All right, later.